Awesome. Can you see my screen?
Yes.
Great. Hi, everybody. My name is Dillon Amaya. I am happy to be here talking with everybody. I'm a research scientist at the NOAA Physical Sciences Laboratory in Boulder, Colorado. And I'm going to talk about something very, very different than what Taylor just presented, thinking about seasonal climate predictability and how that may be changing in the future. I know that many of you are probably interested in sort of that more S2S timescale, so shorter timescales for predictability and prediction skill. But I'm hoping that you'll see that a lot of what I talk about today is going to be relevant for those timescales as well. So I just want to acknowledge also my co-authors on this, folks from University of Colorado Boulder and also NCAR up the hill from NOAA PSL. So when thinking about seasonal climate predictability, seasonal outlooks that are based on historical skill relationships are obviously extremely useful, and they're used all the time for decision making. And this is just an example of one of those seasonal outlooks. This is a precipitation outlook that was issued in September of 2023, so in the lead up to this past year's El Nino event. And you can see that the pattern for precipitation outlook, which was valid for this past winter, DJF of 23-24, you can see it looks very much kind of like our cartoon picture of what we might expect a typical El Nino year to look like. We get wet throughout the American Southwest and dry in the Pacific Northwest and the high northern plains. And so like this understanding and this sort of outlook is built on, hindcast simulations and our understanding of long control simulations and observations of how El Nino is going to imprint on, in this case, US precipitation. And as I said, these sorts of outlooks are extremely useful. They help guide decision-making for a variety of different sectors, but they do have some limitations. Primarily, they represent our understanding of actual skill, which comes from hindcasts or statistical that are either statistical or dynamical in their representation. And for those that may be unfamiliar, a hindcast, as I'm referring to it here, is just a model that's been set up so that it is predicting things that have already happened in the past. And we do that for some set period, and then we look and see how well we predicted the past to get a baseline of what the actual skill for a given model might be when it's trying to predict something in the climate system. But when we think about how models are predicting something and getting this actual skill, they're sort of capped. They're capped by this concept of potential predictability or potential skill, which represents sort of a quote unquote hard predictability limit that's intrinsic to the climate system. It's just basically saying how predictable do we expect something to be just given the chaotic nature of the climate system. And as models have improved over the years, by either improving parameterizations or increasing resolution or just our better understanding of the physics, newer models have increased the actual skill and have started to butt up against some of these potential predictability limits in the climate system. And there are some interesting papers suggesting that we may have reached our limits as far as things like INSO forecasting skill. Of course, the flip side to this, and the reason why I put hard predictability limits sort of in quotes, is this concept of the signal to noise paradox, this idea where there are actually some systems in some parts of the world that we can predict better than we theoretically should be able to. And that leads to this paradox, the signal to noise paradox. This is not the actual focus of my talk, the signal to noise paradox, but I feel like it's at least important to mention and make sure that everybody aware that that is out there just as a concept. But the important thing here is that whether the potential predictability represents sort of a soft or a hard limit to forecast skill in the climate system, it does represent sort of an important goal that a lot of dynamical forecasting systems or statistical forecasting systems are trying to achieve. It's trying to maximize as much skill as they possibly can, given that chaotic nature of the climate system. And what's really important to realize is that potential predictability and, as a result, actual forecast skill is not static in time. It can be affected by internal climate variability. And in particular, it's gone up and down substantially in the past. And as I mentioned, it goes up and down. And maybe one way to illustrate that is from this Lau et al. Paper in 2023, where they were looking at historical forecast skill of Nino 3.4. And this is at 18 months lead. So it's about a year and a half in the future. And this is over a long hindcast period from the mid-19th century through the 20th century and into the early 21st century. And you can see how that forecast skill for Nino 3.4 reached a minima in sort of the mid-20th century. And now we're kind of living in an era, at least we did in the 70s, 80s, and 90s, of particularly high ENSO forecast skill. And they concluded that most of this variability is being associated with natural changes in the climate system, primarily internal variability, leading to these long-term changes in that potential predictability limit and potentially actual skill. But the question I want to ask today is, will seasonal climate predictability change in the future, particularly as a distinct response to anthropogenic climate change? Is there a forced response in predictability? And one reason why we might think that could be the case is that climate models project significant changes to ENSO and its teleconnections going into the future as a distinct response to climate change. Obviously, there's tons of uncertainty surrounding, what will happen to ENSO by 2100 or later. And this figure is just sort of illustrating that for you. It's showing you the ensemble mean boreal winter Nino 3.4 standard deviation. So it's ENSO amplitude in 30-year windows from 1920 to 2100 from 5 climate model large ensembles. So each color is a different large ensemble. The spread of those large ensembles is shading, and the solid line is the ensemble mean. And the black represents the range of uncertainty values for observations of that same quantity. And basically what you'll see is that models super disagree on what the future of ENSO is going to have. Some models say that ENSO amplitude should increase, some models say it should decrease, and some models suggest that it should basically stay the same. But regardless, there's lots of evidence to suggest that ENSO may respond significantly to increased greenhouse gases. So given that ENSO is such an important part of such an important source of deterministic forecast skill at seasonal timescales, if it were to change, then it's not a stretch to think that maybe predictability, or that potential predictability that relies on ENSO and its teleconnections, may also change as a direct result. So the way that we're going to test this is by adopting what's called the model analog framework. For those that are unfamiliar, model analogs are a very old idea going back to the 60s. It's this idea that if two states in the climate system are very close to each other, they can be called each other's analog. And so the idea here is that if you want to predict tomorrow using today's observations, you can go look in a library of data, whether that's from a model or past observations or some other data set, and you can look for instances that look very much like today. And then you can use the evolution of that model or other data products in the past as a forecast. So you can basically create a statistical forecast that's based on these analog matchings. And lots of studies have shown that this is a very efficient, computationally efficient, and skillful way to get forecasts. But whereas a model analog approach is using a model to predict the real world, I'm going to be adopting what's called a perfect model analog approach, where I'm going to use a model to predict itself. And the idea here is that in this perfect world where the model is just predicting itself, that model and its forecast is coming from the same distribution of climate variability. So as a result, it has no biases relative to itself. There's no unconditional biases, there's no conditional biases. And so the predictability estimates that you get out of that forecast estimate that potential predictability, that upper limit. It's telling you how much we could forecast something given the chaotic nature of the climate system and given the architecture associated with that given model. So the objective here is to estimate anthropogenically forced changes in potential predictability using perfect model analogs from large ensembles, like what I showed in the previous slide. And I'll just sort of remind you what those are here. So I'll be applying this perfect model analog method to 5 single model initial condition large ensembles. So there's CSM1, 2, GFDL SPEAR, GFDL ESM2M, and MPI. They have a variety of number of different ensemble members depending on the model. And I'm just sort of reminding you what the Nino 3.4 amplitude trend is in each of these models here. And hopefully you can see my cursor, but so for CSM1, we get an increase and then it sort of levels off. CSM2 is less monotonic. You get an increase and then a decrease. SPEAR is a late 21st century increase. ESM2N is a late 21st century decrease. And MPI is basically not changing. And so given these the spread and sort of the future outlook of ENSO in each of these models, I'm primarily going to be focusing today on these 3 models because they represent sort of the range of possible outcomes that could happen to ENSO. Either it increases, it decreases, or nothing happens. Although I will also show some results for these other 2 models too, if you're interested. So all of the data is going to be regridded to a common 2.5 degree grid, and I'll be looking at predictability changes from 1920 to 2100. And then going forward, I'm just going to drop the word potential. I'm just going to refer to things as changes in predictability or changes in skill. But keep in mind that this is the perfect model world. So everything is potential. It's potential skill or potential predictability. All right. So I do want to take a second and sort of step through my workflow about how I build these forecasts. So just bear with me a little bit. I'll have some examples, but the idea here is that I take a large ensemble, let's say it's CSM1, and I want to extract the sea surface temperatures from that data set for a given 30-year period. Let's say it's 1921 to 1950 from all of the large ensemble members. I'll then remove the seasonal cycle from every ensemble member, remove the ensemble mean, which is a very important part here. So by removing the ensemble mean from every ensemble member, I'm just focusing on, I'm removing the changes in the mean state, but I'm allowing for forced changes in the variability, the rectification of the forced changes in the mean state on the variance. So we are looking at forced changes in predictability, but I also want to, I don't want to predict the trend. So I don't want to, it's trivial to predict over multi-years, you know, the warming trend, especially when it gets strong in the late 21st century. So we're removing the ensemble mean to really look at how changes in the prediction skill of the variability change going into the future. So then given those 30 years in that ensemble, that large ensemble, let's say it's CSM1 again, we're arbitrarily going to take the first ensemble member and we're going to treat it as the quote unquote truth. This is the observations that I want to predict. And then I'm going to construct a data library using the remaining members. So for CSM1, I'm going to try to predict the first ensemble member and I'm going to draw analogs from the remaining 39 ensemble members. And because they're all initialized, you know, long ago with slightly different perturbations, by the time you get to the middle of the simulation, all of these ensemble members are statistically independent from each other. So they represent different planets, different Earths. So they pulling from these different data libraries is a totally justified way to get an independent ensemble of forecasts. So then we're going to initialize a forecast by taking a global map of sea surface temperature anomalies. And then we're going to keep the subsequent 24 months as the target. So I'm going to try to make 24-month forecasts. And so this is just an example of me trying to predict January of 1944 with the first ensemble member in CSM1. And then I'm going to look in my data library of all the Januaries from the other 39 ensemble members and see if I can find analogs that look like this. So I'm going to choose analogs based on RMS error, global RMS error. And then I keep the top 10 and their subsequent 24 months as the forecast. So these are the 10 best matches to January 1944 in the first ensemble member. And this is again coming from the remaining 39 members from CSM1. And you're going to see that there could be the same year, so January 1922, but because they're coming from different ensemble members, it might as well be on a different Earth. But there are instances where you get the same member, but I make sure that they're separated far enough in time that they represent mostly independent samples. So then you can repeat this process, treating each remaining ensemble member as the truth. So before I was trying to predict ensemble member 1, next I'll try to predict ensemble member 2. And I'll cycle through all 40 ensemble members of CSM1 and create a bunch of forecasts. So for CSM1, you end up with 40 members times 12 months times 28 years in a 30-year period that I'm trying to forecast. So you end up with 13,000 forecasts with 10 members each, basically. So you get a 10-member forecast for every initialization in that 30-year period times the 40 ensemble members. So the nice thing here is that because you're using large ensembles and because you're using a perfect model method, you're not dependent on real world observations. You don't have to look backwards and you don't have to use modern era data. You can look into the future and try to predict the model itself in the future, calculate skill in the future, and then see how that predictability is changing going forward. All right, so enough methods. Let's see what that actually looks like. This is going to show you perfect model skill, or potential skill for CSM1 in 1921 to 1950 at 0-month lead. And so what that means is how well is our model analog matching, how well are analogs matching, how well is that initialization matching, and how well is that producing skill. So over the ocean here, this is predicting SST. Over land, this is 2-meter air temperature. And I forgot to mention that one of the nice things about perfect model forecasts is you're just trying to match climate states. So in this case, I'm using SST to choose climate states from my library. But once you choose a climate state, once you decide where you are on the attractor, you can choose any variable that you want to forecast. So in the paper that we've written here, we actually forecast upper atmospheric circulation as well as precipitation. But you're also seeing here that I'm forecasting surface temperature over land, even though I didn't use it to choose my analogs. So it's a very powerful tool to get computationally cheap statistical forecasts. But so as you'll see, this is the forecast skill at 0-month lead. And we can extend this out to 24 months. And you can see that as you go further out in time, the forecast skill goes down, which is to be expected. But you can see that even at 24 months lead, there is the potential in the climate system to predict INSO with significant skill, at least based on the estimate from this particular model. So even if our dynamical forecasting systems that we use today, our traditional initialized forecasts, even if they don't have significant skill at 24 months, this estimate suggests that it's a possibility. If we could just understand the climate system better or represent it with different parameterizations that maybe represent the physics better, that potential is there, which is pretty cool. But this is, again, for the past. So it's the beginning of the 20th century. We can play this same game for the future. So this is representing the forecast skill in the future at these different leads in CSM1 for the period 2071 to 2100. And then we can take the difference in the skill to see how potential predictability is changing in the future in this model. And so based on this one model, surface temperature predictability increases nearly everywhere, but especially at long leads and in the tropics, where the stipples here represent where 80% of the ensemble members in CSM1 are agreeing on the sign of the change. So that sort of represents a robust forced response as opposed to a natural decadal shift between two 30-year periods. But a big caveat to all this is, I started this talk mentioning that the models very much disagree on the sign of future changes for things like INSO. Who's to say they're not going to disagree about the sign of future changes of potential skill? And it turns out that's absolutely the case. So this is the change in potential skill for the MPI Grand Ensemble and GFDL ESM2N. And you can see that for MPI, there's very little change at any lead in potential skill going into the future. But for GFDL ESM2M, there's broad decreases in potential skill for surface temperature going out to 2100. So the sign and intensity of predictability changes are very, very model dependent. And I'll just tell you, and I can show you later if you're interested, but these changes that I'm showing you here are consistent for other skill metrics besides correlation coefficient and other variables. So precipitation, upper atmospheric circulation, sea surface height, etc. So why is this happening? Why do we get such divergent model responses in the future? Well, it all goes back to these Nino 3.4 amplitude trends that I mentioned before. And I'll just sort of remind you what they are for these models. Again, in CSM1, INSO amplitude increases in the future. For MPI, it basically stays the same. And for GFDL ESM2M, it decreases. And INSO, as many of you I'm sure are aware, as I've said before, is by far the most important source of deterministic forecast skill on these timescales. It is the thing that we latch onto historically to give us something that we can trust in a forecasting system. So if INSO, which is wielding its hammer, is increasing its amplitude, it's wielding a bigger stick, a bigger hammer, and potentially ringing in the climate system harder when it happens, increasing your signal to noise ratio in the forecast and potentially making your forecast more deterministic, and vice versa for a decreasing INSO amplitude. And this is something that we can explicitly test too. We can actually calculate the signal to noise ratio of the forecasts in the early part of the 21st century or 20th century versus the end of the 21st century. And we can see how that signal to noise ratio is changing in each of these models as a way to glean whether these forecasts are becoming more deterministic and therefore more skillful. And in the case of CSM1, the signal to noise ratio increases in a pattern that looks very much like the changes in the skill. And I'll just tell you, and I can show you if you're interested, but I'll just tell you that the change in the signal is about 5 times larger than the change in the noise. So the ensemble mean forecast amplitude is increasing by about 5 times larger than the change of the denominator, which would be the noise in the actual forecast. So the forecast spread isn't increasing as much as the forecast ensemble mean, which is a sign of increased determinism, which is interesting. But that signal to noise ratio change is consistent across the models, where MPI, before it showed basically no change in skill, you're basically getting no change in the signal to noise ratio, and ESM2M saw a decrease in the skill, but also now a decrease in the signal to noise ratio. So just to sort of summarize this relationship between Nino 3.4 amplitude and skill, I'll do that for these five different models that I mentioned before. So now bringing in those other 2 models that I haven't shown yet. This is a constellation plot. It's basically showing you the relationship between Nino 3.4 amplitude and globally average sea surface temperature skill in each of these models. where each marker is a different model. And the shading of each marker is telling you it's telling you what that value is for a different 30-year period over which I made that calculation for. So for 1950, this is the period 1921 to 1950. So the year you're seeing here is the end of that window. 2100 is the period 2071 to 2100. So let's just look at CSM1 for a second. It's the circles. You can see that as you go forward in time, as you go from the purples to the yellows, Nino 3.4 standard deviation increases, and as you do that, globally average skill goes up at 6 months lead. For ESM2M, as you go from the purples to the yellows, you get a decrease in amplitude, Nino 3.4 amplitude, and a decrease in skill. And even for models with sort of modest changes in Nino 3.4 amplitude, you see this imprint on skill as well. So for like CSM2, you get this non-monotonic increase in Nino 3.4 amplitude that then in the mid 21st century starts to decrease, and you see that sort of arc pattern in skill. So this is certainly a first order process when it comes to predictability, Nino 3.4's control over it. And so this relationship also, as I mentioned, is being driven through changes in the signal to noise ratio of these forecasts, where this plot down here is now just showing you the same sort of idea where Nino 3.4 amplitude is being related to changes in globally average signal to noise ratio. And you can just sort of, by following a couple of these markers, you can see that they have a similar trajectory as the changes in the skill. And this is also true at these other leads. I just focused in that 6-month lead, but this relationship holds going out to at least 24 months. So just to sort of summarize for you very quickly, potential predictability, it will likely change in the future as a distinct response to anthropogenic climate change that's as opposed or in addition to natural decadal fluctuations in potential predictability that are just driven by internal variability. The sign and intensity of forced predictability changes are linked, and that's associated with the sign and intensity of forced INSO variability changes going into the future, as uncertain as those are. So even though the future of INSO is extremely uncertain, if we can constrain the future of INSO, we're going to have a much better idea about what's going to happen to predictability. And the important thing here is that we are beginning, depending on your read of recent papers, we are beginning to have a better sense for what INSO may be doing in the future. There's lots of recent studies that have suggested that INSO amplitude is likely to actually decrease in the future, especially going beyond 2100. And I'm referring to the Svengel et al. 2021 paper, but there's others I can reference you to as well. But the important part here is that if INSO amplitude decreases in the response to future climate change, then historical forecast scale relationships that we depend upon, or we have depended upon in the recent past, they may not hold going forward. And so this is where I think this is super relevant for the S2S community as well, is that even though the S2S community, as far as I understand it, even though there are other sources of deterministic forecast skill on those timescales, things like MJO, INSO is still an important part of that forecasting space. So here's where I think it could be relevant to the sort of that week 3-4 community as well. So one more thing I want to mention is just another plug for the power of model analog forecasting. An interesting question you could ask is, how well can these large ensembles that I'm using, how well can they actually predict the real world? Up until this point, I've just been showing you forecast skill of the model predicting itself, but how well could it actually predict the real world if we applied the normal, quote unquote, normal model analog framework, where we use observations as our initialization, where we're trying to predict the trajectory of the real world, given some trajectory in the model. So we're going to do that just to illustrate for you what that looks like. I'm going to show you the multi-model mean SST skill, so sea surface temperature skill, from dynamical forecasts from 6 NMME models. So if you're unfamiliar, the NMME is the North American Multi-Model Ensemble of models. These are operational dynamical forecasting systems that are used to make many of these seasonal outlooks that I mentioned before, including the seasonal precipitation outlook that I showed on my very first slide. So these are sort of the gold standard, what we use here in the United States to make decisions. And then I'm also going to show you the multi-model mean SST skill from the 5 model large ensembles based on model analog forecasts that are being drawn from, being drawn by ERSST v5. So in both cases, I'm using NMME or the model analogs to predict ERSST v5 from 1991 to 2020. So here's what that scale looks like. The left column is the multi-model mean for the large ensembles and the model analogs. And the right column is the multi-model mean from the 6 NMME models. And basically what this tells us is that model analog forecasts are, at least for SST, and at least on these timescales, are as skillful as dynamical forecasting models. And they're infinitely cheaper. I can run model analogs on my laptop in 2 hours. I created this figure generating thousands of forecasts in a couple hours. Whereas NMME requires, I'm not, very importantly, I want to mention that NMME is an incredibly important and useful tool, and I'm not advocating to get rid of any of these things. I just want to highlight the power of some of these computationally more efficient tools as, an extra member of the ensemble that could be used in consideration going forward. All right, so I will leave it there. I'm happy to answer any questions. If you don't have a chance to ask me something, or you can come up with another thought down the line, please feel free to shoot me an email. Thanks.
Great, Dillon. Yeah, I quite enjoyed your talk. And at this moment, any questions from the audience? Yeah, again, our discussion document is open to everybody, and I'll put in the chat box as well, in the chat, so you can utilize, put any comments or questions. So I have 2 questions, Dillon. So I'm not in the field of atmospheric science, but is there any utility of AI or machine learning to merge or train large set of atmospheric model ensemble for weather forecasting?
Yeah, I mean, yes. The short answer is yes. There's all sorts of groups trying to utilize machine learning or AI to improve forecasts.
Mm-hmm.
I'm on a paper right now that is using machine learning to improve the way in which we select model analogs. And the idea being that if we can optimize the weights that are used, the spatial weights that we use to select climate states in a model analog framework, then we can improve the forecasts in model analogs. And basically what the paper shows is that that is the case. We can get about a 10% improvement for something like Nino 3.4 forecast skill by applying machine learning to the model analog selection process.
Okay. Yeah, thank you for the detailed answers. And another question is that any computational cost. So what kind of parallel computing techniques are used and which servers are used? And maybe my questions are too specific.
For the model analogs?
Yes.
So I run everything on Casper, which is one of NCAR's supercomputers. And I actually don't run any parallelization. This is all very hard coded, mostly because I'm not the most efficient coder, but I'm sure you could make it more efficient and make it even faster.
Me neither. Yeah. So when I worked at NASA Goddard, the people helped me to parallelization. But anyway, yep, me neither too. So anyway, I quite enjoyed. So yeah, another question. It was in the document. I have looked at the potential predictability of CESM1 in comparison to other models. For example, ECMWF, ERA5, I believe, and CESM1 has much more potential predictability on the S2S timescale than the ECMWF. So I think it's a kind of comment. So. Okay, yeah, we are running out of time. So thank you to the presenters today. Again, speakers will address the discussion document even after the webinar, and I will explicitly ask them. So therefore, please add any questions or comments on it where the presenters will contribute to them. So our next webinar will be on May 6, 2 p.m. Eastern Daylight Time. So thank you and see you later.
Thanks, DK.